This meeting is being recorded.
So welcome to today's GOAT seminar. Today's speaker is Tung.
So hi, my name is Tung, and I will be talking about capacitated case center in realistic settings. But first of all, bribes are in order. So please have one and pass it around. What is up, my gluttonous goats? So let's do it. Let's go. So what's the problem, right? So I'm given on input a graph with some edge weights or edge lengths, an integer k, and a capacity, which is an integer which every vertex has at its disposal. And this is and on the figure we have an example of such a graph. So these numbers next to vertices are capacities of the respective vertex, and here I define k to be 2. All right, so this is my input to an integer k, capacity for each vertex, and some underlying graph. And what is it that I'm doing? What I want to do is to find a subset of vertices of size at most k, and find an assignment of all vertices that are outside of k to vertices inside of k, so that if for every vertex inside of S, number of vertices pointing to it by this assignment phi is at most its capacity. And so I find such an assignment, and I'm looking for an assignment of minimum distance between a vertex and whatever it is mapped to. Okay. So here, let us take a look at 2 examples. So here, so the colors are not great or whatever. So here is an example where we choose these 2 vertices as into our set S, and now whatever is inside of this ball is assigned to this vertex. Whatever is inside this ball is assigned to this vertex. Makes sense? And there should be some, yes. And so this is a nice solution and all, but it is not feasible because this vertex's capacity is 3, but there is 1, 2, 3, 4 vertices pointing to it. So this is not a feasible solution. So here's an example of a different solution which is feasible because this vertex is now assigned here. And now the cost of this solution is the maximum distance between a vertex and whatever it's pointing to, which is this blue path. Okay, so this blue path induces the cost of my solution. Makes sense? All right, good. So what is known about this problem is that, well, this is like a very specific type of problem. If the capacity of every vertex is like essentially unbounded for our purposes, then this is the well-known K-center problem, which is like dominating set with edge weights, if you will. So how do we solve this problem? Well, we kind of don't, but because this problem is NP-hard, which means that we cannot solve it optimally in polynomial time, given some reasonable assumptions. So what do? We look for approximations, right? So here's a picture version of the definition of approximation algorithm. So a C approximation algorithm gets an input and outputs a solution whose cost is at most C time worse than the optimum in time, which is polynomial and the input size. Okay, so standard definition. And if you are really ambitious, then what you go for are polynomial time approximation schemes, turned into PTAS, where on input you receive in addition a positive epsilon, and now your solution has to be at most 1 plus epsilon times worse than the optimum, and the time has to be polynomial in the input size, and you treat epsilon as a constant. So for an example, a running time of n to the 1 over epsilon is perfectly valid. Make sense? All right, so how are we doing? So it is known that this capacitated K-center problem admits a constant approximation with constant of 9. On the other hand, it is known that, and perhaps this is not very surprising, that there is no better than 3 approximation for this algorithm unless P equals NP. Yeah, by some standard reductions, I would say. So that's the state of the art as far as polynomial time approximations go. But I'm like a very greedy person, and I really want the p-test, right? So what can we do? We can restrict our set of inputs. And so can I? So the question is there some setting where I can overcome this 3 minus epsilon approximation lower bound, which is like realistic, such as planar graphs, Euclidean spaces, or real world, whatever that means, and so on. So let us see. Yeah, so talking about special settings. So special settings for me in this talk are going to be the titular doubling dimension and highway dimension. I will define them shortly, much to some of your dismay, but let's see. So doubling dimension for now, you should just see as some generalization of Euclidean spaces. All right, that's all you need to care. All you need to know. And what is in this table? So in this table here on the left, we have types of problems which come primarily from like network design and clustering settings. And here is the running time of the best known approximation scheme for the problem in the left column. So for an example, for K-center, we have an approximation scheme for K-median, K-means, and so on. And TSP, we all have like approximation schemes of varying quality, but they exist for doubling dimension. Of course, varying quality means that these two are like well, here in this social group, I would say that these are like kind of parameterized, right? If you think about it, and this one is very much not parameterized. This is like quasi-polynomial approximation scheme. So yeah, and so here comes the second part, which is highway dimension. And highway dimension, for now, all you should think of is that it somehow captures properties of transportation networks. And so here we have corresponding approximation schemes. But one thing I would like to point out is that these last two results were obtained by taking these results for doubling dimension and somehow mangling them to work in the setting of highway dimension, which should be somewhat surprising because if we have time, I will show you the doubling dimension and highway dimension are incomparable parameters. And like a fun fact, highway dimension is like incompatible with like anything you've ever heard of, you can think of. So that's why highway dimension is worth studying, because it's it's realistic and it captures strange properties, but and it is not comparable with anything else, so it's good. All right. So what did we do, right? So first of all, yeah, let me just to truly appreciate what we did. Let me make one more definition. So an efficient parameterized approximation scheme, or an EPAS, is a polynomial time approximation scheme, but now an input in addition to the instance and epsilon, I receive some parameters of the input, right? Like, and what do I want? I want again a solution that is at most 1 plus epsilon times worse than the optimum. But now the running time is restricted to be polynomial in the input size and some function of the parameter at epsilon. So for an example, I don't know, 2 to the parameter times n to the 1 over epsilon is not allowed anymore, because epsilon is now appears somewhere near in the exponent of the input size, which we don't want. Okay, so I want the epsilon also to be, or the dependence of the running time on epsilon also has to be some computable function. Okay, makes sense. If you are a huge fan of parameterized algorithms, you can view epsilon as one of the parameters on our input, then everything makes sense. Modulo encoding and stuff. So so but I don't care. So So these three algorithms are EPASs because the running time does what we want it to do. But this one is very much not an EPAS because both highway dimension and epsilon appear in the exponent of the input size. Okay. Okay. So what did we do? So first of all, we show that if I want to go, we show an algorithm for capacitated K-center in the setting of low doubling dimension graphs by adding some observations to this algorithm and improving it in many ways. And now, so given the state of the art and the cultural context and stuff, one would expect that these arrows are preserved. That that if I found an algorithm here, I can somehow do some magic and find corresponding algorithm here, right? But our main contribution is in some sense like cultural, in the sense that we show that there exists some constant such that you cannot find an approximation, even for a constant epsilon, you cannot find a parameterized approximation scheme given some reasonable complexity assumptions. Okay, so just to reiterate the main point is that that up until now, if one wanted an algorithm, meaning an approximation scheme for low highway dimension graphs, what one would do is to look at what's the state of the art doubling dimension, take that algorithm and somehow mangle it to work for highway dimension. But now we somehow give some evidence that this is not always the case, and sometimes one has to be a bit smarter to get an algorithm. So that's the main contribution. Okay, so now we will proceed to the technical part of the talk. So any questions as to what's and why's?
Like C and epsilon is like kind of
Uh-huh.
there is exists C, no C approximation, and there is O epsilon.
Yes, so in particular this epsilon, I can treat this epsilon as a constant, right? So even if this algorithm, if I allow this algorithm to have running time n to the 1 over epsilon, then even then I can't find an algorithm which has k and highway dimension as like parameters and find that correspond.
Epsilon is something like C minus 1.
Epsilon, oh yeah, sure.
Oh, okay.
I mean, right. So the main point is that, what we are looking for approximation schemes. Of course, if you set C to be 9, then of course such an algorithm exists, right? Because a polynomial time algorithm exists. But here, what I want to stress out is that you cannot hope for an approximation scheme, which is, the best type of approximation algorithms, right? Right. All right. So technical part of the talk starts now. Are we okay with that?
But for this K-median, this could still happen also for capacitated case, and right? The same kind of algorithm as we have for
Here?
K-median or K-means, yeah.
Yeah, it is possible that this algorithm exists, but it's like 1 year old result. So who knows what's like maybe this guy was too lazy to finish it. I don't know. So okay, so shall we proceed to the technical part? I mean, questions are welcome because you will delay the pain.
And the question, do we have to, is not allowed.
Yes, okay, so doubling dimension. So that's the definition, right? I give you some metric space, and now a ball of radius r around vertex u are simply a set of vertices that are at distance at most r from u. It's exactly what you would imagine a ball is. So what is doubling dimension? Doubling dimension of a metric space is the smallest constant delta, so that if I draw any ball of any radius around any vertex, then I can cover it with at most 2 to the delta balls of half the radius. So here in this picture, this blue thing can be covered by 1, 2, 3, 4, 5 balls of half the radius. So so we can guess that so this delta for this particular ball would be logarithm of 5, if it's like 2 or something. So this is doubling dimension, pretty like,
It would be 3 because
upper bounds or zeros, whatever. Oh, yeah, sure. Yep.
Why is it not a real number?
Are you a what?
Why
because you don't want to have real numbers.
Because I mean, what is a real number, right? No, no. So I don't know. I mean, for me, graph parameters are usually integers, and that's, I would say, the main reason.
For me, capital delta is always the maximum degree of the graph.
Yeah, but I mean, I'm probably from a too cultured part of track to understand that. All right, but so why I studied doubling dimension? Because if you look at this picture, then you can kind of realize that if you look at d-dimensional LQ metrics, then they have doubling dimension d. So this is not some complete absurd parameter, but this is like well motivated, generalizes known stuff, and so on and so forth. Okay, so that's why this is worth studying. And yeah, so here we go. So highway dimension, right? So let me first make an intermediate step to higher dimension. So suppose you have an edge-weighted graph, and now let's fix some scale R. And the way you should think of R is some zoom level onto your graph. So for example, on this picture, we have a part of the transportation network of Prague, meaning public transportation network. And if I increase R, then I zoom out from Prague, and now I can obtain like the railway network of this entire country. And if I increase R even more, maybe I get the train network of entire Europe and stuff like that. Okay, so this is what R is. And now if I fix a zoom level, then I define PR to be the set of paths such that their length is at least R and or strictly more than R, at most 2R, and this 2 is some arbitrary constant. And moreover, these paths have to be shortest between their endpoints. And how you should think about it is that fine, I'm looking for a path, a shortest path between 2 points. So I open my map and I zoom so that I can actually see this path. And if the path is too short, meaning it's shorter than R, then I need to increase the zoom to actually see something. If it's more than R, then I should zoom out. And this is the way you should think about it. So this is like the set of shortest paths. And what is the shortest path cover? The shortest path cover is simply a hitting set for this set of shortest paths. Okay. So to recap, I have my graph. I zoom into it and now I collect some shortest paths which still fit in this map. And now I make a hitting set. And that's my shortest path cover. And what this should illustrate is that the shortest path cover tries to capture the property that there exists some set of points in your transportation network such that if you want to take a shortest path between any 2 points in this map, then you must pass through one of these points of the shortest path cover. That's what it's trying to capture. Makes sense? And intuitively you would think that this is like reasonable, right? Because if you want to go somewhere in Prague from here, you either go to Lotyšska or Davidska. And if you go from Malá Strana, you go to Malostranska or to US and stuff like that. So this is like, reasonable thing to consider. Okay. Okay, so now we go to finish the definition. So what's highway dimension? Highway dimension is the smallest integer such that no matter how you zoom into the map and no matter where you look from, then if you stand somewhere and you look at in radius 2R, then you will see at most this many points of the shortest path cover. So what we are measuring is somehow the local sparsity of your shortest path cover, which somehow corresponds to the fact that no matter where you want to travel, the number of decisions, like which way, through where do I have to go, is bounded. If you want to go somewhere in Prague, right, you don't consider, oh, well, now I walk to Staroměstka and I do something, right? I go to Davidska, which is 1 point, or Lotyšska if I want to take the tram, or if you are unfortunate and you live at Strahov, then you take a bus, I guess. But it is like 3 decisions or something. And it is conjectured that real world, no matter what it means, has bounded highway dimension. Okay, so this is the definition of highway dimension. It's essentially some sparse or fair hitting set for the set of shortest paths, and you take many copies of this shortest paths because you can do different zoom levels onto your map. Okay, this is any questions? All right, so congratulations, you can forget what highway dimension is, because what I want to show you is how this algorithm for capacitated case center works in the setting of low doubling dimension metrics. So let's first forget capacities, because it's like nasty, and let's think of case center, right? Let's forget capacities. So in this case center, so what does the optimal solution tell me, right? Of some cost opt. Well, this optimal solution tells me that if I draw balls of radius opt around these optimum centers, then every vertex of the graph is covered. So that's what it tells me. And to get an algorithm, I defined something called a net. So a net of a metric space is a subset of points, which first informally they cover this entire graph in the sense of case-centric covering, but they are sparse. So the first bullet says that for every point of the metric, there has to be some net point nearby into my net that I choose. And the second property says that my net points have to be well spaced. Okay? And of course, this epsilon times opt is like chosen for my purposes. You can create a net for any number you want. And one thing to observe is that you can compute a net greedily, right? I just take, if I want a net of an epsilon of net, then I stand at the vertex, I carve out a ball of radius epsilon times opt, I throw it out, and I keep doing this. And that's how I obtain my net. Okay, so in each vertex in which I stand and do this carving, that I put that into my net. Make sense? Okay, so what's next? So, suppose that I know where the optimum solution is. If I take this optimum solution and I replace it with its nearest net point, and I increase the radius from optimum to 1 plus epsilon times optimum, then that's a valid then it's a valid 1 plus epsilon approximate solution, right? Makes sense? Yeah, just like by this picture or whatever. So right. So of course, the main problem is that we don't know where the optimum solution is. Otherwise, we are done. But what I can do is that, okay, I don't know, but I will guess. I will guess where they are. Or in particular, I will guess which net points contain the optimum solution nearby. So how does the algorithm work? First, I guess the value of the optimum solution, which is some intervertex distance. There's polynomially many of them, so I'll just try them all. And once I have this optimum, then for every subset of the net of size at most k, I try these net points. I try to draw balls of radius 1 plus epsilon times opt around them. If this entire graph is covered, that's my solution. If not, then I just keep going. Okay? And this is like a good algorithm by this thought experiment here. So of course, this algorithm has some kind of a downside, that its running time is size of the net choose k, right? So that's a bit of a problem, because the net can have size like n or something like that. But very fortunately, there's a theorem which says that if your metric has the following property, that it's give me a second. Yeah, that the minimum distance between 2 points is let's say 1, and the maximum distance or its diameter is also bounded. Then if I capture this number by alpha, then the number of points that can be in this metric can be bounded by logarithm of diameter times doubling dimension and exponential in this number. Okay. And to think of how you would get this, think of how you would prove this theorem, right? I prove it by induction on the radius of the graph. So first I take the entire metric, and I know that if I draw a ball which covers the entire metric, that there is a bounded number of balls of half the radius which cover it. And now I apply induction in every one of them, and I add it up. So that's why this theorem makes sense and is not unreasonable, because this is what doubling dimension precisely captures. It bounds the growth of your metric. Okay. So with this theorem in mind, so let us look in one of the balls of the solution. Okay, and let us look at the net points in this solution. So in this ball, the maximum distance between any 2 points is 2 times opt, right? 2 times the radius of the ball. And the minimum distance between any two net points inside this ball is epsilon times opt, because that's how I defined the net. So now I know that my alpha, known as aspect ratio, is 2 times 1 over epsilon. So, and this theorem tells me that inside this ball of the optimum solution, there is at most 2 to this number of points, so that inside one of these balls there's at most epsilon 2 or 1 over epsilon to some constant time doubling dimension. And what's that good for? Well, because remember, what is the k-centered solution? It's some set of balls which cover my entire graph. So if I want to bound the size of the net, what do? I take this theorem, I slap every ball, and now what I get is that the size of the net is k for every ball times 1 over epsilon 2 delta. Okay? But now like, we are clear, because now we have an algorithm which or now the super polynomial growth depends on k, epsilon, and doubling dimension, which is an FPT algorithm or FPT approximation algorithm. Makes sense? So this is the starting point. This is very, like this is not the most complicated algorithm in the world, in my opinion. So it's so let's. Or is it complicated, Ishan? I don't know what you teach in this AG1 of yours. Like this is not an AVL3, I'm sorry. So, okay. So this is some sort of algorithm. So let's think of capacities, right? So if I want my this algorithm to support capacities, what can go wrong? So one of the steps of the algorithm is that I take these optimum centers and I replace them with the net points. But it may happen that this net point here, which I want to use as a replacement, has much lower capacity than the original optimum center. That can happen, right? So what do? Well, if I guess correctly the ball, which contains an optimum center in it, then I know that there must be some center inside this ball which contains a vertex of capacity at least whatever I need, because in particular the optimum is in it, right? So before I took this optimum center and I rerouted it to this net point. So now I do one more step. Around this net point, I look for a vertex that has the highest possible capacity, and instead of rerouting the optimum center here, I reroute it from here to here. So this in particular, so originally I had a solution of cost at most optimum. Now I add 1 epsilon factor for getting to the net point. I get another epsilon factor for getting to the vertex with the highest capacity, and I have a solution which has cost at most 1 plus 2 epsilon times optimum, which is still fine. All right. So here's now our new algorithm. So first, for every subset of size at most k of the net points, and for each vertex in this net, and for each net point, I look from it at a vertex which has the highest capacity that is nearby, and I add that to my solution. And of course, now the question is like, what does it mean for some points to be a solution? Because before in k-center, we were looking for covering of the graphic balls. Now we're looking for some assignment. So there's some. So how do balls correspond to functions? I will show that later. But this is like the main. So the main new idea is on this line number 5. You just look for, instead of replacing optimum centers with net points, you replace optimum centers with some guy who has the highest possible capacity near the net point, and you still get a 1 plus epsilon approximation. Right. So second problem is that, okay, so I do this replacement, but what if, like for some unknown reason, there are like 2 optimal centers inside this ball, right? Then this algorithm may not work, but because this replacement might not be valid enough. But the fix is simple. One uses multi-sets. So what do I mean by that? So for each subset of net points, which is now multi-set, so I can pick 1 point multiple times into my solution. I look again for the vertex with the highest capacity, which I have not used yet, which is captured by this. So in this S, I look for my solution, and I add those vertices with the highest capacity, which have not been used yet, which is this set minus S. Okay, and and then I proceed as before. So it's like not very complicated. And okay, so now I can deal with capacities, modulo some details which are not important. And one last problem to resolve is this like set of question marks. So if I give you some points, how do you know if they form a feasible solution of some cost? And you can think of like all kinds of like insane algorithms, but yeah, so this is the formal definition. But what I did was that I used network flows. So I give you some points and I ask you, do these points form a solution of cost C? Then I create a network so that on the top layer, I have all vertices that are outside of S. In this layer, I have vertices that are inside of S. And from each of these vertices, what's the main problem is that I want that the number of vertices from V minus S pointing here is at most its capacity. So from this vertex U to the sink, I add an edge of capacity, whatever its capacity is in the input graph. And now how do I complete this graph? So for this pair of vertices, if their distance is at most 1 plus 2 epsilon the optimum, which is what I'm looking for, then I add an edge of capacity 1. If the distance is more than that, I don't add in the edge. And this is how, if I give you some set of points and I ask you, does a solution of cost 1 plus 2 epsilon opt exist? You create this network flow and you ask, is there a flow of size this much? Okay. And that's it. So this is the entire algorithm. So you guess the cost of the optimal solution. Now you iterate over multi-subsets of your net. And for each once you have this multi-subset and you determine that, and you get some points, you compute some network flow. And if this network flow is like of large enough size, you return the assignment which corresponds to the flow. So if the edge is saturated, that's the assignment, and so on and so forth, and that's it. That's the algorithm. Okay. Oh yeah. So that's it. So conclusion. So what did we do? So I just showed you this algorithm. This reduction is technical, and there's like nothing particularly interesting in it. What this paper, which contains these results, has. This paper is actually a bit more like, so this algorithm is a simpler version of what we actually did, because so if you think of, if you want to model some problems case center and you want to like place some hospitals to serve some households, then a case center solution can tell you that, all right, let's place this hospital in this guy's living room because that's the best position, and that is like not great for some reasons. So what we actually looked at was the problem called case supplier, where the set of vertices where you can put the solution and the set of vertices that you want to cover are two disjoint sets, or they can be disjoint, which is it is not immediately obvious that such a thing would exist, but it does. And also, if so if you look at case center, like as forget capacities, like imagine you have some nice solution for case center, right? And now I come in and I put a vertex like somewhere behind the door. Then suddenly, like your solution has to also account for that guy, and and your solution can blow up. So and in the set, and this is like dealt with in the setting of like clustering with outliers. So there is a version of this problem which also tells you, all right, find a feasible solution, and you are allowed to ignore like some number of people of vertices, like 10 or 20, some parameter many, and in that case, this algorithm can also work, whatever that means. And so the main contribution, to sum up, is like this cultural remark that if one tries to, that if it is not the rule that every approximation scheme for doubling dimension graphs has its counterpart in the setting of low highway dimension. And yeah, so that's it. Thank you for attention.
Questions?
Did you like the cookies?
Yes.
Okay.
That's a good question.
You can bring them next time. That's it.
Well, if you remember the definition of higher dimension until next time, I will give you a cookie. I'm closing the slides now.
Real time.
Exactly. Exactly. So here's the FAQ, so a fully anticipated question. So, let's look at this algorithm for low doubling dimension, right? And so I told you the doubling dimension somehow generalizes Euclidean spaces. So some of you know that for Euclidean TSP, we actually have a PTAS, right, which runs in polynomial time, but this monstrosity is quasi-polynomial. So the question is, can this be improved? And the answer is yes. So like 10 years ago, there was an improvement. Some people took this algorithm for Euclidean TSPs, and they turned it into a p-test for doubling dimension graphs. And the question that I'm dealing with right now is that fine. So there's also some quasi-polynomial monstrosity. So can I also get a p-test if a p-test exists here? Of course, this result says that maybe not, but we are hopeful that the answer is yes, actually. That there exists a TSP algorithm in low highway dimension, p-test for low highway dimension graphs, and that's my hope. So that's one open question that I'm dealing with right now. And once I have it, then I have a TSP approximation scheme for the real world, and I can buy, and Amazon will pay me enough money to buy this school and fire all of you.
Any other open questions? All right, so let's thank the speaker again.